the applications, many functions arise as inverse of other functions. This is the case also for some elementary functions, such as the logarithm function, which is the inverse of the exponential. Given a function f, we denote its inverse by the symbol f to the minus 1. The goal is looking for a rule to express the derivative of the inverse in terms of the derivative of f. Let's start by recalling two important facts about the inverse function. The first is that every strictly monotone function on an interval I admits a natural inverse. If we denote by j the range of f, the inverse of f is a function defined on j with values in I in the following way. Fixed any b in j, consider the horizontal line of equation y equals b, and observe that this line intersects the graph of f at a single point p. The value of the inverse function at b is precisely the horizontal coordinate of this unique intersection point, namely f to the minus 1 at b is the unique solution of the equation of x equals b. In summary, f to the minus 1b is a if and only if fa equals b. We observe that each of the two functions undoes the effect of the other. In fact, given any a in I, substituting b with fa in the first equality, we get f to the minus 1 fa equals a. Similarly, f of f to the minus 1b equals b for every b in j. The second fact has a geometric nature. The graph of f and the graph of its inverse are reflections across the bisecting line y equal to x. This means that if a point of coordinates AB belongs to the graph of f, then the reflected point of coordinates BA belongs to the graph of the inverse of f, and vice versa. We are now ready to state the theorem on the derivative of the inverse function. Let f from I to j be a continuous and strictly monotone function, and let f to the minus 1 be its inverse defined from j to I. Assume that f is differentiable at a and set b equals fa. Then, if f prime at a is not 0, the inverse function is differentiable at b and its derivative is 1 over the derivative of f evaluated at a. Therefore, to obtain the derivative of the inverse of f, it is enough to compute the reciprocal of f prime. However, pay attention to the fact that such derivatives are evaluated at different values. If we want the derivative of the inverse at a certain value b, we must calculate f prime at a, where a and b satisfy the relation b equals fa, or a equals f to the minus 1b. This is the point to pay most attention to when using the formula. Let's see an example.
Let's compute the derivative of the natural logarithm function as inverse of the exponential function. To this end, we denote the exponential by f and the logarithm by f to the minus 1. Let's first fix a positive value b. To get the derivative of f to the minus 1 at b, we need the derivative of f. So, f prime of x is equal to the exponential of x. We have to evaluate such derivative at a certain value a, which is related to b by this relation. That in our case means that b is equal to exponential of a, or equivalent, a is the natural logarithm of b. So now we can compute f prime in a, which is exponential of a, that is b. Since f prime at a is not 0, we can apply the inverse rule to get f minus 1 prime in b is equal to 1 over b. Our calculation holds true for every fixed positive b. Hence, we conclude that the derivative of the natural logarithm of x is equal to 1 over x for all x positive. This is how we prove the rule for the logarithm that we find in the table.
But where does the formula for the derivative of the inverse come from? We can find it out having in mind the geometric meaning of the derivative, which represents the slope of the tangent line to the graph of the function at the corresponding point. Here we see the graphs of f and its inverse, which are reflections across the bisecting line y equals x. We now draw on the graph of f the point P with coordinates a, b, and the tangent line at P. The slope of this tangent, let's call it m, is given by f prime a. In our case, f prime a is different from 0, so m is not 0. Now, draw on the graph of the inverse the point Q with coordinates ba. Of course, the tangent line at Q has slope given by the derivative of the inverse at B. Let's call it big M. Now, since the graphs of f and f to the minus 1 are reflections across the bisecting line, the two tangent lines are reflections as well. This is the key property. It is in fact known from analytical geometry that the slopes of two straight lines, which are reflections over the bisecting line, are reciprocal of each other. That is, big M equals 1 over small m. But big M and small m are exactly the derivative of the inverse at B and the derivative of f at A. This is where the inverse function rule comes from.